Wake up, Marvin. We need to escape Ursius very soon. There is an existential threat of an alien species called Mus'ab invading our planet.
Oh, from Earth? Those guys are very dangerous. I guess it is time for this useless pile of metal to finally end its life.
Never fear, my dear. My PhD in orbital mechanics can surely help us. Earth will be saved.
What do you even learn with a PhD in orbital mechanics?
Well, for one, you learn about the orbit of planets. For the longest time, it was a mystery. The ancient Greeks had many different models, but by the end of the 1500s, the most widely accepted model was the geocentric model, where the Earth is at the center of the universe. Then a guy named Nicholas Copernicus had an idea. What if, instead of the Earth being at the center of the universe, the Sun was at the center of the universe? This was called the heliocentric model, and most people did not accept it because that would mean that as the Earth moves across the orbit, the position of the star would slightly shift across the night sky. And this is a phenomenon known as stellar parallax.
Wait, isn't stellar parallax actually a thing already used by astronomers on Ursius?
They did not detect stellar parallax because their instruments were not precise enough. Back then, their technology sucked. For goodness sake, how do you even live without YouTube? But anyways, then Johannes Kepler became the disciple of Tycho Brahe, who was the most famous astronomer at the time. And Brahe did not want Kepler to overtake him, so he gave Kepler an impossible task. Find out why the orbit of Mars and Mercury are so weird. You see, back then, people believed the orbits are perfect circles because, the planets were created by God, and circles are the most perfect shape, and God would never do anything imperfect. And so, in order to account for some of the discrepancies produced by this circular model, things like epicycles were added, but nothing could really explain Mercury or Mars well. Brahe was working on his own model, but his was based around the geocentric model. Now, Kepler, on the other hand, really loved the heliocentric model, and so he approached this impossible problem with that model, and eventually it led to his groundbreaking discovery of the three laws of planetary motion. Now, ironically enough, Brahe ended up making Kepler the most famous astronomer of his age. Now, the three laws of motion go like this. 1. Planets orbit in an ellipse, not a perfect circle, where the sun is one of the focal points. Now, 2. If you think of the orbital ellipse and you divide it into segments of equal areas which stem out from the sun, then a spacecraft will travel an equal area in an equal time. And third, the square of the orbital is proportional to the cube of the length of the semi-major axis of an ellipse, which essentially means it's the radius of the long side of the ellipse. This solved the problem of Mars's orbit because while most planets have a negligible difference in terms of their deviance from a perfect circle, which is also known as eccentricity, Mars has a high eccentricity. Newton looked at Kepler's work and asked why. Whether or not the apple fell on his head, Newton realized his answer in the form of the law of universal gravitation. Essentially, all objects attract each other, and the force of attraction is dependent on their mass. This produced a problem for Uranus and Mercury, though. Their orbits deviated significantly from the models, even with Newtonian physics. Now, a person called Urbain Le Verrier solved Uranus by realizing that another planet was in our solar system, and we now know that this planet was Neptune. After the discovery of Neptune, this method was used to suggest that there was another planet between the Mercury and the Sun, or maybe a group of planets between them. Nobody really knew, but there was a general sense that something was there. And so they called this planet Vulcan. Yet, as we now know, Vulcan doesn't exist. Einstein came in and solved this problem by rethinking gravity, and he did it in a geometric sense. He wondered how an object falling feels no force, yet is still accelerating. His solution was that space and time are kind of like a fabric of reality, and this is called space-time. Now, in a flat space-time, an object just wants to go in a straight line, but gravity curves and warps space-time. So, as the object is trying to travel in a straight line, its straight line gets bent because of gravity. He also realized that time travels differently in the warped space-time. And I went into a huge rabbit hole trying to understand the math itself, but I realized you probably need a master's degree to really understand the math.
You humans and your puny brains can't even comprehend basic math, and I thought you had a PhD.
Let's talk about the different ways of calculating motion. Newtonian mechanics are really useful when working with Cartesian coordinates. Here, motion is caused by different forces acting upon one another. So if you know the position of Earth at its aphelion, and you calculate all the forces acting upon it for a given time period, you can use F net equals to ma to find Earth's acceleration. And then you multiply time to find the velocity, assuming that the acceleration is constant. This velocity can tell you where the Earth will be next. But you realize that for motion, all you really need to know is the velocity and position of the object. This is where Lagrangian mechanics comes in, and this is named after Lagrange, who also discovered the Lagrangian points.
Will you bore me by talking about a ripoff of classical mechanics, or talk about something more fun, like Lagrangian points?
Be quiet, little bot. I'll talk about Lagrangian points soon. Anyways, Lagrange really... Hey, who turned off the lights?
Must have been the snow, of course. Yeah, the snow.
How am I supposed to talk about useless information without lights?
Maybe talk about something useful, stuff that could actually save us.
Listen here. If I wanted to learn anything remotely useful, I would have gotten a job instead of going for my PhD. Any questions?
Humans and their consequences have been a disaster for the natural world.
Fine. I'll do some research and get back to you in a few hours.
What have you found?
Okay, well, I have decided to learn about orbits. First, let's go over some satellite orbital mechanics. Most satellites and their planets can be thought of as having a circular orbit, and a circular orbit is another case of centripetal rotation. This is where the centripetal force is the force that points inwards, and so the acceleration also points inwards. And this is a perpendicular to the velocity, which points tangential to the circle. And this has the effect of changing the direction of the velocity, but not in the magnitude. In a circular orbit, the energy levels remain constant throughout the orbit. There are also many orbits that are considered elliptical. Here, the direction of the velocity remains the same as they occur in circular orbits, but the magnitudes change. The closer the orbit is to a gravitational body, the faster it is due to Kepler's third law. This is also reflected in the energy, where the kinetic energy is greater the closer you are to a gravitational body. And since mechanical energy is conserved, that means the potential energy must be less the closer you are to a body. No, the Lagrangian points are 5 points between a gravitational system of two objects, where the gravity of both objects and the centrifugal force balance out. meaning that you can stay there without having to expand fuel. Take, for example, Ursius and Sewell. L1 is between Ursius and Sewell, L2 is on the other side of Ursius, L3 lies beyond Sewell in the opposite direction. Now these three Lagrangian points are unstable, meaning any influence from any outside force will throw you off of the Lagrangian point. Now L4 and L5, these are the stable Lagrangian points. And that means that even if there's a slight drift, or maybe the force of gravity from Jupiter is acting upon you there, you will still stay in the Lagrangian point. The Lagrangian points are found by making an equilateral triangle between the Lagrangian point, the Earth, and the Sun. As for orbital maneuvers, there are a few to think about. First of all, there's the Hohmann transfer orbit, which is the most famous of the orbital maneuvers. You want to make your periapsis the starting orbit or the ending orbit, depending on whichever one is lower. And then you want to make the apoapsis of your transfer orbit the other orbit. So then, this is essentially the most fuel efficient way to get from one planet to another in most cases. But if there's a planet in between the two the two planets, then a gravity assist may come in even more fuel efficient. This is essentially taking in the angular momentum from a planet and then borrowing it to essentially change your direction and oftentimes even velocity. And this requires little to no fuel. The third type of orbital maneuver is a bielliptic orbit. And this is done in 3 burns. The first burn, you raise your apoapsis very high, very, very far. Then you go to the apoapsis, and then you change your periapsis to the desired orbit. And then you go to your periapsis, and then you bring your apoapsis back down to your desired orbit.
So what's the plan?
We should land on an asteroid in the Lagrange points.
We have the power to move across entire galaxies, and you want to simply move to the Lagrange point of the Earth's solar system?
Look, I did not get a PhD in intergalactic travel, okay? Although, you give me an idea. What if we destroy Earth before they destroy us?
I like that idea. Let's fire up the liver of silver right now. And the system's ready. Everything's set up. Alright, now shoot. In 5, 4, 3, 2, 1. Fire!
Let's go! I hit Earth. No more shall Mus'abs attack us.
You hit Earth? Alright. But in the wrong universe. What is wrong with you? How did you hit the wrong universe?
Oh, shoot. I think we're screwed.
Do we have another projectile?
No, we only bought one.
Maybe the Lagrange point idea wasn't so bad after all.